This is section 1.5 in our textbook, Linear Dependence and Linear Independence. If V is a vector space with an infinite field, then there are no finite subspaces other than the subspace, which is the trivial subspace, consisting of the zero vector. And to see why, well, if W has a non-zero vector in it, then it has AW for all A in the field. So all subspaces of an infinite vector space are also infinite. And it's our challenge to find the smallest finite set of vectors that will generate or span that subspace. So suppose that S is a set of vectors in W, and that the span of S is W. Our question is it the smallest it could be, or are there vectors that we could omit from S and still keep a span of W? Well, if there are vectors in S, V1 through Vn, and scalars, not all of which are zero, and we can express the zero vector as a linear combination of those vectors from S, then in that case, any one of the vectors with non-zero coefficient could be written as a linear combination of the others. Just move it to the other side and you have a linear combination. And we could remove that vector from the set S and obtain a smaller spanning set for W. For example, in R2, the plane, if we set up this equation here involving three vectors, A1 and constants A1, A2, A3, we can find infinitely many non-zero coefficients that would satisfy this equation. One of which would be A1 is equal to -2, and A2 is equal to 4, and A3 could be -2. So filling in the coefficients A1, A2, A3, you have then this sum here of three vectors that gives you the zero vector. And notice that we can take one of those vectors and solve for it in terms of the other two. That's all this is saying above. If there is such a non-trivial representation of the zero vector in S, we say that S is linearly dependent. We also say that the vectors in S are linearly dependent, meaning you can get a non-trivial linear combination of those vectors that will give you the zero vector. If there is not a non-trivial solution, in other words, if whenever you choose a set of vectors, a finite set of vectors in S, and you write this linear combination here, AV1 plus A2V2 plus A3V3, etc., and set it equal to the zero vector, there is no non-trivial solution. In other words, it implies that all of the coefficients are zero. That certainly is a solution, but it's called the trivial solution. In this case, we say that S is a linearly independent subset of V. We say that those vectors are linearly independent, and we say that the set S is linearly independent. For example, in R2, the plane, if we set up this equation, taking the two vectors 1, 0 and 0, 1, you know that this equation has only solution A1 equals A2 equals 0. So these two vectors are linearly independent. Another example, in the set of polynomials of degree less than or equal to 3, P3 of R, the vectors, I'll put them in braces here, the vectors x cubed, x squared, x, and 1. That is a linearly independent set. Or we could say that those 4 vectors are linearly independent, meaning that if we set up an equation, a1 times x cubed plus a2 times this vector plus a3x plus a4 times 1, and set it equal to 0, the only solution is the trivial solution. a1 equals a2 is a3 is a4, and they all have to be 0. So this is the kind of question in this section that you have to answer, and I think many of you, once you see how to set it up, you could answer it without looking at this video. So if that's the case, fast forward to the next example. Or maybe do the problem and make sure that you can answer the question. I'll do it for you, and I think many of you probably need the review. So to see if they are linearly dependent, we always do the same thing. a1 v1 plus a2 v2 plus a3 v3 equals the 0 vector. And we see if we can solve that for a non-trivial solution. So this will give us a set of 3 equations in 3 unknowns, and we have to solve. So the first thing we do is set up the 3 equations. And I think I would put plus 0a2 in here so that I have I have a1, a2, a3 in each equation. I want to solve those 3 equations simultaneously, so I am going to just use a vector of their coefficients instead of doing so much algebra with the variables. So this is the matrix of coefficients, of the coefficients that we're looking for. And we want to row reduce this matrix. There are 3 things that we can do. One is we can take any equation and multiply it by a constant and add it to another. Another thing we could do is divide through by a constant or multiply by a constant. And the third thing is, of course, we could change position of the rows. So the first thing I want to do, I need to have a 1 in the upper left corner here. So I've already got that. Now I will use that row on the top to eliminate -1 and 2. In other words, to make those rows have a 0 in the first column. So to do that, I would take the top row and just add it to the second row, leaving the top row the same, and then I would multiply it by -2, multiply by -2, and then add. So I'll do that now. Doing so, we get this matrix. Notice I multiplied the top row over here, the top row on this matrix, top row multiplied it by -2 and added it to the third row, thereby giving me a 0 in this position. -2 times 2, -4 plus 2 is -2. Multiplying -1 by -2, I get, by 2. Whoops. Okay, that's a mistake. Multiplying by -2 here, I get +1. I'm glad I checked that soon. -2 times -1 is 2 plus -1 is 1. So I get this matrix. What this means is that this, if I were to replace these as coefficients for A1, B1, C1 and write out equations, those equations have exactly the same solution as the one we started with. Now, the next thing I want to do, I need a 1 here. So that's easy. I'll just multiply through by 1/2, getting this matrix. Now I will use the second row to turn the other entries in the second column to zeros. So I will then multiply the second row by -2 and add it to the first row, and I will multiply it by +2 and add it to the third row. The second row stays the same. And we get this matrix. Notice we made all of the entries in the second row 0 except for in the second row. All right, so now I need to get a 1 right here. So I'm just going to multiply that row by 1/2, getting this new matrix. Now I will use the third row, I have a 1 there now, to eliminate the entries in the third column other than 1. So I'm going to multiply that row by -1/2 times -1/2 and add it to the second row. And then I'm going to multiply it by 2 and add it to the first row. And then I will get the identity matrix to the left of the vertical bar. Now, if this is what happens when you try to solve the equation, you see we have solved it. This implies that A1 is 0, A2 is 0, A3 is 0. So we know that the three tuples that we started with are linearly independent. Just read the question again. It says, is this set of vectors in R3 linearly dependent or linearly independent? And we set up this equation, and we found that A1 must be 0, A2 and A3 must be 0. So the answer is they are linearly independent. Here's another example that you might be able to just fast forward through. Do be sure that you can set up the matrix of coefficients. But once you can do that and you know how to solve it, just fast forward. This is asking us if this set of 4 vectors, polynomials, in this vector space, the set of all polynomials of degree less than or equal to 4, are they linearly dependent or linearly independent? So I should have put the word linearly in here. Sorry. So let's set up an equation that we need to solve in order to find the answer to that question. So we set up this equation, A1 times the first polynomial plus A2 times the second plus A3 times the third plus A4 times the fourth, and we want to know if we can find a non-trivial solution for A1, A2, A3, A4. In other words, not all of them are 0. If we can't, then we will say that the polynomials are linearly independent. Make sure that you can set up this matrix. And you know, when you have all zeros, when you're solving a system of equations to see if for linear independence, you don't really have to put the column of zeros, but I'm just doing it for now so that you'll see exactly that the matrix there represents each of those equations. So look at row 4 here. It's the same as row 3. If I divided it by -2, these two rows would be identical. So I'm just going to cross out one of them. We don't need that. So we have a 4 by 4 matrix. And we want to do row reduction, it's called, and see if we can get a non-trivial solution. I have 1s right in the positions I want them. I've got 1 in the A1, the 1-1 position. I have 1 in the 2-2 position. I have 1 in the 3-3 position. So that's really nice. This will probably go quickly. I already have zeros in column 1 other than the 1, and I need to get 0 here and 0 here. So I will use row 2, and I will simply add it to row 1 to get rid of the negative 1, and I will multiply it by 3 and add to the 4th row. Doing so, I get this matrix, and I see that I have my 1 where I want it, and now I want to use row 3 to eliminate the 2/3, the negative 1/3, and the 4. I want to turn those into zeros. So I will multiply the 3rd row by negative 2/3 times negative 2/3 and add it to the 1st row. I will multiply it by 1/3 and add it to the 2nd row, and I'll multiply it by negative 4 and add it to the 3rd row. That will give me zeros in the 3rd column other than the 1 that we have. So this is the matrix that you get after doing those 3 row operations. And we immediately see that we are not going to be able to get 1 in the 4-4 position. So A4 could be absolutely anything. And we can solve this equation right now. Let's write what each of let's put it back in terms of equations now. Equations just involving A1, A2, A3, A4. This means that A1 minus 4A4 is equal to 0. A2 minus 3A4 is equal to 0. And the 3rd row gives us A3 plus 3A4 is equal to 0. And A4 is a real number. So we get a solution then. A1 is equal to 4A4. A2 is 3A4. A3 is negative 3A4. And A4 is any real number. So we have infinitely many solutions to this equation that we wrote out. One solution, let's let A4 be, that was A4. Let A4 be 1. And we get the solution 4, 3, negative 3, 1. And you can try that back in the original problem here. Let those values of A1, A2, A3, A4 be 4, 3, negative 3, 1, and see that yes, indeed, you get the 0 polynomial. So we say that these vectors are linearly dependent. Theorem 1.6, let V be a vector space and S1 be a subset of S2, a subset of V. If S1 is linearly dependent, then S2 is linearly dependent. Well, since S1 is linearly dependent, this implies that there exists a finite number of vectors, V sub I goes from 1 to n, such that there are scalars A1 through AN, not all 0, such that A1 V1 plus A2 V2 plus ... plus A sub n V sub n is equal to the 0 vector. I equals 1, 2, up to n, and not all A sub I equals 0. So A sub I is not equal to 0 for some i's. Well, all of these, since S1 is contained in S2, this linear dependent set of vectors is also in S2. Therefore, S2 is linearly dependent. remember, to be linearly dependent for a set to be, all you need is some finite number of vectors where you can get a non-trivial representation, a linear combination equal to the zero vector. Likewise, if S2 is linearly independent, then S1 is linearly independent. So in S2, for any finite subset of vectors v1 through vn, a linear combination of them equal to the zero vector is trivial. a1 through an must be 0. Well, then certainly if we pick any subset of vectors in S1, if we change this to S1 here, this is also a set of vectors in S2. So if we pick these vectors in S1, the linear combination equal to 0 has only the trivial solution because those vectors are also in S. The last thing that we'll do in this video is prove Theorem 1.7. Let S be a linearly independent subset of a vector space V, and let V be a vector that is not in S. Then the set S union V, the set containing V, is linearly dependent if and only if V is in the span of S. So what we're asking is in here is, when we add a vector into a linearly independent subset, how can we tell if the set remains linearly independent? So first, let's suppose that S union the set containing V is linearly dependent. Then there exist V sub I, vectors V sub I, in this set S union the set containing V, such that a finite number of them, let's say n of them, such that there exist scalars a1 through an and a1 v1 plus a2 v2 plus up to a n v n equals 0, and not all of the a sub i's are equal to 0. Not all. Some of them are not 0. Well, we know that S is linearly independent. So that tells us that one of these vectors has to be V. They cannot all be from S. So one of the vectors V sub I, one of the V sub I with non-zero coefficient must be the vector V. So I'm going to write WLOG without lack of generality. Suppose V1 is equal to V. And A1 then we know is not 0. Well, that means then that A1V, which is A1V1 up here, is equal to minus A2V2 minus A3V3 minus dot 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 minus A sub n V sub n. And we can solve for V. A1 is not 0, so I can divide by it. Minus A2 over A1 V2 minus A3 over over A1 V3 minus dot 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 minus A sub n divided by A1 V sub n. We have just written V as a linear combination of vectors in S. So V then, we can conclude, therefore, V is in the span of S. And that's what we wanted to prove. Now we need to prove in the other direction. We need to prove that if V is in the span of S, then S union the set containing V is linearly dependent. Okay, so we're assuming that V is in the span of S. So V in the span of S implies that V is equal to B1, let's say U1 vector, plus B2 U2, plus some finite number of them, let's say M, B sub M, U sub M, the vector, where the U sub i's are vectors in S, and the B sub i's are, of course, from the field that's over the vector space, the scalars. Okay, well then that means that B1U1 plus B2U2 plus B sub M U sub M, that's V. Let's subtract V minus V, then that's equal to a zero vector. And the coefficient of V is -1. So we have a linear combination, a non-trivial, let's say this is a non-trivial representation of the zero vector. Therefore, S union the vector V is linearly dependent.